Good morning. Welcome to Krishna's classroom. Today we discuss the generalized dominated convergence theorem and also the continuity of integration. Now we first, it's just a generalization of the dominated convergence theorem that we have just now proved with a more general condition, which is whose special case would be the dominated convergence theorem. I'll make a remark about it. So we'll state the theorem. Now let us state the theorem. Let Fn be a sequence of measurable functions on E that converges pointwise to pointwise almost everywhere to F on E. Suppose there is a sequence Gn of non-negative measurable functions on E that converges pointwise almost everywhere on E to G and dominates Fn in the sense that this is the important. Mod Fn Gn on E if limit n tending to infinity G, that is G is integrable, then now this is the statement of it. How does this differ from the dominated convergence theorem that we have looked at? Only differs here. So every Gn is assumed to be a G. Okay, it's a non-negative measurable function on E, and that dominates Fn. That is, mod Fn is less than or equal to G. G is integrable. I mean, that's the only difference. So remark, we get that's the only difference. Okay. Now we prove more or less along the same track as we did in the other case. I mean, this is quite simple to prove. Proof is, if you, it would be nice if you compare the proof of these two. Consider the sequence. Gn minus Fn. And this is, of course, measurable functions, and Gn converges to G almost everywhere, and Fn converges to F almost everywhere. So, see, we can drop that almost everywhere condition from it. There is no harm, because we, for the sake of the proof, we assume that it is true everywhere on E. Otherwise, what you have to do is just take E and throw out from it the what is called the set of measure 0 on which this does not converge to G, does not converge, Gn does not converge to G, and Fn does not converge to G. So, and work on that. So it's all the same. So without loss of generality, we are assuming that everywhere on E, these conditions are satisfied. By Fato's lemma, we just apply the Fato's lemma. If we apply Fato's lemma, we will get the one part of the inequality. To come to the one part of the inequality to get the conclusion. Now then this is what happens. The consequence of the Fato's lemma is less than or equal to and this of course is equal to when because of the sign minus sign here, it becomes lim sub. Here of course we had integral g because gn was equal to g in all cases, therefore we had limit of this is essential that's equal to integral over e. That is the case in the dominated convergence theorem that we have. Now this is equal to, see that this is, since this converges to integral of g minus now this you can apply linearity. Applying linearity, lim sub integral over e fn is less than or equal to integral over this is the first inequality that we have. Further, what you have is this. By Fatos lemma again, we have integral over e so this is another inequality that you have, and therefore what you have is the following, that is called, so these two blocks, these two identified inequalities give you, so together we have but we have the general inequality, namely that lim inf hence what you have we have lim inf and that's equal to, but this, this is the condition that the limit exists. Okay, therefore follows that. Therefore, you have so that completes the proof of this theorem. Okay. So that's the generalized bounded convergence theorem, where you see that in the original dominated convergence theorem, the original dominated convergence theorem, what we have assumed is, if we set Gn equal to G, in the general dominated convergence theorem, if we set Gn equal to G, then you get the dominated convergence theorem. So that's a very special case. So that completes the proof of it. Now we introduce the two things. One, of course, countable additivity of Lebesgue. Now recall that this is what you have. Suppose disjoint collection of measurable subsets E and E is equal to it's a countable union of disjoint countable union of En. So we have this is the assumption that I intersection J for I not equal to J. This is the assumption that, okay. Then what we want to observe that this is it. Then what we want to observe is that the integral of f of an integrable function on E is the countable sum of the integrals of f on En. Okay, so that's what you have. So you have, we expect the countable sum this is indeed so. So that's what we want. Okay. So this in fact is a sort of continuity for us, because you see that E is equal to En. And what you have is this. You can write En as union of k equal to 1 to n E. Then you see you get a telescopic sequence of measurable subsets of E, whose union would become the whole of, so it's something like this. Okay. Now what you have is that on each of these regions, EI or En, you have the integral of f, and the limit of that is essentially equal to the integral of, so this is sorry, not this. This is not true. This is not true. This is not true. What you have is this. So you see, you have the if you want, you can use some other notation, that is okay. And then of course what I have is this, that is Fn is contained in Fn. This is the sort of relation that, and then you can talk about the integral over Fn of f, and this converges to integral over E. This is what we are going to. Okay. So, so this is now, see, this Fn becomes a telescopic. So it is something like this. That this is your Fn. Eventually, this goes to union n equal to 1 to infinity En, which is equal to E. Therefore, what we want to show is that sum of the or the integral over each of the Fn is equal to, goes to integral of f over, as Fn is monotonically increases or converges to E. That's the theorem that we want. So let us state the theorem. Let f be integrable and En be a disjoint collection of measurable sets. E whose union then what you have is this. Now this is the continuity. Countable additivity. Okay. Right? It's a countable additivity. So we shall prove this. As I said, you can define Fn as the union of Ek from k running from 1 to n. Then you have a what you call an increasing sequence Fn with the property that Fn is contained in Fn plus 1, and then you can show that integral over Fn over F is equal to integral over E over F. But this, of course, you can, Fn is the union of a disjoint collection E1, E2, etc. En, and therefore that becomes, you see, the summation integral over Fn is going to be the summation over from 1 to n equal to or k equal to 1 to the integral over Ek of F. Sorry. That's it. So let us prove this here. Proof. So we let n be an integer, be a natural number. Now define the sequence Fn to be F multiplied by the characteristic function of En. That means the function is equal to F on En, and outside it is 0. Okay. That is a characteristic function. Therefore, see that Fn is equal to F on En, and outside it is 0. Okay, I think slightly sorry, right here the define Fn now chi n, not by chi n, and chi n we have to say chi n is the characteristic function of Pq, which I have designated here as Fn. Okay, so this is equal to, in the discussion that we had previously, this is of course equal to Fn, and therefore chi n is essentially the characteristic function of okay. So what we now do is the following. Then what about these Fn's? Fn measurable functions sequence of measurable functions on E and you see that mod Fn is less than or equal to mod. That's clear. Now what we assume is that Fn converges to F almost everywhere pointwise. This follows from the definition of Fn. On because Fn is equal to F on small fn is equal to F on capital Fn. Okay, so this is the structure that we have. This is your E, and here it is small fn is F here, small fn is fn plus 1 is F here, and so on. So you see that it converges to F on E pointwise. That is clear. Now by Lebesgue dominated convergence theorem, now dominated convergence theorem on F on Then what we have is that, see, you can check that all the conditions are fulfilled to apply this theorem, and the conclusion of this is going to be integral over E of. But what is Fn? Fn is actually, so see, this is what you get. Therefore, this is equal to limit n tending to infinity of integral over f into chi of Fn. Fn we have defined. Okay. And what about this? This is equal to limit n tending to infinity of, what about this? This is equal to integral Fn f. And what is Fn? Fn is equal to Fn is equal to following. And that's equal to limit n tending to infinity of integral union k running from 1 to n, that is Fn of f, which is equal to limit n tending to infinity of, this is a finite sum, have sigma a equal to 1 to n. Now you see that integral over and therefore you see that this is equal to take the limit, this is the infinite sum that you have, and so this is equal to limit n tending to infinity of, okay, now this limit is essentially this is that is the proof. Okay, so that completes it. Now next we look at the continuity of integration. So we have two parts for this result. one part for an ascending sequence of measurable sets, the other one for a descending sequence of measurable sets. Okay. So the first part of the statement is this. Let be an ascending collection of measurable subsets of it. In fact, we have used this result in the previous year. Okay. The second part is for descending sequence. Measurable sets. So in both these cases, we apply the earlier technique and bring it to the application of dominated convergence. So what one does is the following. Now what we do is the following. That means you have En and union En is equal to E. Now what one does in this case is the following. We define Fn as f times characteristic function of E. That is, the function is f on En and outside it is 0. Now one immediately observes the following. That means the you have mod Fn mod F. So Fn is a sequence of measurable functions with this property. That means it's all dominated by mod F, which is integrable, and that's the assumption that we are making. And therefore, what you have is the following. That means integral and that of course is limit n tending to infinity integral over n. Now this is the statement of the first statement that you, and in the second case assume En is because here we are assuming f is an integrable function. Okay. So this assumption is that assume is a descending sequence of substance. That means you have the following. That is, if En this is what. Now write once again. Write by you. Now you see that once again you have this is fine. Okay. Therefore, once again you can apply the dominated convergence theorem by what we have is this. And that's equal to limit n tending to infinity integral that is C n this is the condition. Therefore, this is so that completes the proof of this theorem also. Okay. Thank you very much. And we conclude at this stage, and we meet again more convergence problems. Thank you.